In this example problem, we want to know how much energy is needed in order to raise a certain mass of ice at a certain initial temperature to steam at a certain final temperature. Alright, so if we draw our graph, we're going from here at some T initial. We have to raise the temperature up to the melting point. Then we have to phase change it from an ice cube into water. We're then going to raise its temperature again, and then once the temperature reaches the boiling point, we can turn it or add energy in order to turn it from a liquid into a gas, so turn it from water into steam. And then we can finally go to some final temperature that we're asked to in the problem. That means that since we're starting here at some initial temperature as a solid and we're going to a final temperature as a gas, we have 1, 2, 3, 4, 5 Q's that we need to add together to find that total amount of energy we need to add into the system, or the heat. So I have up here the heat to change the temperature of the ice. I have the heat in order to phase change, so fusion. The energy to change its temperature is water. The energy to change it from a liquid to a gas, so vaporization. And then finally to change its temperature as steam, or as a gas. Now the mass doesn't change here, so for all of these I'm going to be plugging in the same mass, remembering to convert it from grams into kilograms. So I've looked up here the specific heat of ice, and I've done my temperature change from my initial temperature up to the melting point of the ice, which is 0 degrees Celsius. I've then looked up what the latent heat of fusion is for water, which is this here. Be careful to make sure that you're in joules per kilogram, so make sure you always check the top of the table to see what units you're given things in. I'm then going to add the mass times specific heat of water, and then our initial temperature, we started at the melting point and we're ending at the boiling point. Now I can phase change from a liquid into a gas. So I'm going to take my mass times my latent heat of vaporization this time. So notice that's it's a different number and it's a much bigger number. And then finally it's now steam. So we can take that mass times the specific heat of steam. Now be careful. In your textbook, there's actually 2 values for steam. We're using the one in parentheses, which is the one's at constant pressure. And we'll learn in the next chapter why we use that specific heat versus the one that's not in parentheses. So for the gases, always use the one that's in parentheses. And then we're going to go from the boiling point up to the final temperature. I've then multiplied each of the terms together individually. That way you can check your work as you go through. And then finally added them all together to get the total energy that needs to be added to the system. Now this problem actually illustrates why it is far more painful to get a steam burn than it does to get a burn from boiling water. And the difference is the last couple of energy terms here, where this is the energy you're adding in to raise it up to the boiling point. So if you just have boiling water, you would not do the next 2 Q's if you're trying to stop at boiling water. You have to add more energy into the system in order to then phase change it. So you have all that extra energy that would be transferred from the steam to the person, which was why steam burns are worse than boiling water burns, even though they're at the same temperature. Because steam has the same temperature as boiling water as it's going through the phase change. Now you can add more energy to raise the temperature of the steam, but if you're just in the middle of the phase change, the temperature is going to be at the boiling point. So you have this extra energy in the steam, which then gets transferred to the person when there's contact. So keep that in mind. Steam burns are always going to be worse than boiling water burns because you've added more energy into the system.